Hello. I've been writing code in various languages for some years now, mostly C, but I never learned assembly language. Sure, I could spot some basic features like unrolled loops and vectorized code, but I couldn't write any. Everybody I talked to about it insisted I'll never need to read it, let alone write it, so it's a waste of time to learn. The former statement, that I wouldn't need to read or write it, may be true, depending on the work I'm doing. But after sitting down and learning it, I absolutely disagree that it's a waste of time to learn. No matter what programming language you're writing, it turns into binary at some point, and learning to write assembly code has just reinforced my innate feeling that it would be good to know how it works exactly. Learning it has been easy, actually. After a few days of practice, I'm quite confident I could implement most of the stuff I could write in C. It would be very far from optimal, but with some more practice, I could get it to work, I think. The x86 instruction set we'll be looking at today has hundreds of instructions, but you only need to know a handful to write whatever you want. A lot of them are for very specific use cases, and most instructions simply have many variants for different for different uses, such as aligned or unaligned memory access. Many instructions are obsolete. First, I'll show you how I've linked this assembly program on the right to the C program on the left, and explain how this trivial exponent function works. Afterwards, I'll touch on the specific example that highlighted for me how crucial for my programming skills it is to learn this stuff. As you can see, I can call this assembly function directly in C. Setting this up is easy on Linux. On Windows, simply install WSL in PowerShell. The Windows subsystem for Linux is a Linux virtual machine you can install directly from Microsoft in PowerShell with a few commands. Anyways, here are the files in the folder. I can directly invoke GCC on the C file and the assembly file together, and it produces a finished executable by compiling each of them into objects and linking them. So there's the executable. I can run it and say 2 to the power of 2 is 4, 2 to the power of 4 is 16, 2 to the power of 0, 2 to the power of 0 is 0, yeah. So in this case, the exponent function is an exported function in the object file produced from the assembly code. I can look at the exported symbols with the readelf command, so I will just run the assembler now on the exponent assembly code, and oh, yep, and I should be able to look at the sections. Yep, there's the exported exponent ASM version function. Like we can see over here, it's the same as the label name, and it's the same as what I invoke in the C program. The C code also gets compiled into an object file which references the exponent function, and the linker copies them into one binary, resolving the memory addresses of the symbols. GCC invokes both a compiler and a linker to do this. I'll now explain how the exponent function works line by line and show the C version that I wrote alongside it. The first thing is the ABI. You've probably all heard of an API, an application programming interface. An ABI is an application binary interface. This one is called the System 5 ABI and is common in Linux. There are many ABIs, and you can mix them if necessary. It describes how to make a function call. You make a function call by loading the arguments of the function into the correct registers. In this case, it's RDI and RSI. The third one would go into RDX. When you jump to the address of the function, then you jump to the address of the function here, exponent ASM version. The label just translates directly to memory address, by the way. The caller and the callee need to coordinate on how to handle the stack memory as well. Some calling conventions, including System 5 when you have more than 6 parameters, demand that function arguments be written to the stack, but that complicates things a bit, so I'll ignore it for now. RBP holds the base pointer, and RSP holds the stack pointer. I'll explain both shortly. You see that the very first instructions here save the base pointer with a push instruction and copies the stack pointer into where the base pointer was. Here. With these two registers fresh on our minds, let's divert our attention to how the stack works. Skip this part if you know how the stack works. All professional programmers across most languages have almost definitely heard of the stack, but how does it work? The stack is a region of memory high up in the virtual address space that gets allocated when the binary is loaded. I won't be covering virtual memory in this video. The kernel is stored above, near the top of the memory, and further down in memory towards the lower addresses, one will encounter the heap and everything else. You may have heard that the stack grows downwards. What does that mean? It's simple. RBP, the so-called base pointer, which always points to the beginning of the function stack memory. And yeah, there's the RSP, which points to the end of the function stack memory. When I call a new function, I save the base pointer with the push instruction. The push instruction, here, this one, right at the beginning of the function, it writes to the push instruction writes this to the address in RSP and subtracts the size from RSP. So yeah, it's 8 bytes in this case, since RBP is a 64-bit pointer. So the old base pointer, this one over here, gets pushed to the stack, and then 8 bytes get subtracted from RSP, and then we write the RSP into the RBP. It becomes our new base pointer, as you can see over here. Now RSP is moved into RBP and it's our new base pointer, and this is our new stack frame. And this is how we use the stack. We just subtract from RSP and use the base pointer as the starting point to write anything in there. Just like this, you just subtract from RSP. Yeah. And the next function that comes after it does the exact same. And returning from the function is the same, but in reverse. You can see that over here, RBP is moved back into RSP. So this, our RBP, becomes the stack pointer, pointing, like the beginning points to the end of the old one. And then we restore the base pointer back from the stack. So this one that we squirreled away, that we saved away over here on the stack, it gets popped back into this location, into this register, and RSP goes up again, back over to where it was. So we restore everything to the black area how it was originally when we go backwards in reverse. And then, yeah, that's how it works. And that is, yeah, let's go back to the exponent function. You can see how I bring the stack pointer back to the base pointer, then pop the old base pointer back into RBP. If I wanted stack space, I can do that now. Then I just allocating stack space. All I do is subtract however much stack space I want, 16 bytes, for example, from the stack pointer. And yeah, that's it. Whenever I push and pop more stuff into the stack pointer, it'll change again. I just have to remember to, everything I push, I have to pop back in the opposite order. And here I've manually done these 16 bytes over here. I just need to add it back when I'm done to bring the pointer back to the same place, and then we're good. But we can ignore all that for now. That's basically just how the stack works. Just a little bit of arithmetic on these two pointers, and that's it. I don't even need any of this, actually. I can delete all that. Delete all this stack management. Save it. And compile it all. And the exponent function should work the exact same. Yep. can still get my exponents. We don't even need to do any stack stuff in this function. I was just showing you how it would be set up. It'll still compile and work without a base and a stack pointer, but that's an explanation of the stack. So I loop by jumping, here's the first loop. I loop by jumping directly to a label. Like this loop that goes on until the result of this decrementation operation is 0. And these are local labels. Unlike the exponent ASM version label up here, these are completely local labels. They're not exported to the linker. And here 0b means the first 0 label backwards. It's just how it works. When the decrement reaches 0, we return. The return value is in the RAX register. The caller function main from our C program expects the return value to be in RAX because that's the ABI calling convention. This multiply instruction takes one operand, multiplies it by the value in the RAX register, and writes it back to the RAX register. So we're multiplying the value in RDI by the value in RAX and storing it back into RAX. The special case that the exponent is 0 is also handled. Yep, over here. And there are no if statements. Conditional branching in assembly language works by setting flags in a special register called the flag register, or flags register, during arithmetic operations, then jumping to the addresses if certain flags are set or unset. For example, here we jump to the label if the result of the arithmetic, here, in both cases actually, we jump to the label 1f in the case that the result of the previous arithmetic operation was 0. That's what this JZ instruction is, jump if 0. So if the result of this operation was 0, it sets a flag in the flags register. This one sees the flag, and if it is 0, it jumps over here to 1. And that's how we handle our special case. If RSI, remember the second input parameter, the exponent over here from our C function, if that's 0, we jump down to the special case, and that's how branching works in assembly language. So yeah, and once again, labels are just memory addresses that we've named. I'll leave the C version, the C equivalent, so to speak, open on the left. Feel free to pause the video now and compare them. Hopefully this sheds some light on a few things for you, but this is just the trivial example. The less trivial examples highlight even more esoteric wisdom. Here is our second program. Finding the first occurrence of a character in a string is traditionally an easy problem, right? Here's a simple example. Anyone who's touched code at all, even a beginner, can probably interpret this and see what it does to find the first occurrence of a character. Well, wrong. It's not quite as simple as any programming language would make it seem. The general purpose registers, like RAX, are 8 bytes wide. Instead of reading each character individually, got a diagram here. Here's our example string where we want to search for a character. Instead of reading each character individually out of memory, we can explicitly load 8 characters at a time into one register, RDX in this case. We'll see that in the code again soon. These are our chunks, so to speak. Then we bit shift and compare each character in the register until we've tried all of them. To move to the next chunk, we advance the pointer to the string. The pointer is RDI in this case, which is the first input parameter to this function. See, in C land over here, we right over here we pass in a pointer to this string, and that pointer actually gets incremented by 8 in this case, because that's the size of the RDX register, 8 bytes. And And to move the, yeah, we just advanced the pointer, that's it. I'm going to look at the character search code again, and you can pause the video and see if you can make sense of it. Remember that the right operand of an instruction is the destination. So I'll give you a minute. All right, you done analyzing that? Do you understand these instructions? If you're as intelligent as I am, then you'll be very confused. We can compile this with debug information. So I'm going to do the same thing again. Find char .c, and we want to compile the find char.s and output it to char. And I want to compile it with debug flags like this. And we can just pop that straight open in GDB. Like this. Give it, we want the test string, and we want to search for the character. Let's search for S. We set a breakpoint on find char. Remember, that's the actual name of the symbol over here that's being exported, like we saw earlier, and it's the name of the function that we call in C. So I'm setting a breakpoint on that and running the program. So here we are in GDB. You can, if you look right at the bottom over here, you're able to step through each and every individual instruction one after the next, and it shows you all of the source code and everything. And even better, you can print individual registers like this, and you can, that's the value of the RAX register right now. I can even show all of the common registers over here. These are like all the important registers in x86, all the ones you'll be using most commonly. Like, look, here's the E flags register with all the flags. Yeah, and what else have we got here? RAX, RBX. Here's the parameters, RDI and RSI. RDI is going to be a pointer to the string. We can just like print out that string over here. If we cast it to a character pointer, I think this should work. Yep, that just printed out the test string. So the RDI register is holding a pointer to the string that we passed in from the command line, actually. And we can also print out the contents of the RSI, the character that we're searching for. Cast it to a character. And we search for the S character. And I can just let this program run to completion. And the result is 2. It found the S character at index 2, which would be 0, 1, 2. That's correct. Yeah, so that's compiling it with debug information. I should even be able to object dump all the entire binary, and we can look into that a little bit as well. Dump. Here we go. So if we go to, this is like the disassembly of the executable file that we've created. Here is the find char function that was written by hand by me. Here is the find char simple version that was compiled from the C program. Back over here, this one. This is what the compiler produced out of that. Now, bear in mind, this is not optimized assembly. This is running without optimizations. This is in debug mode, actually. So you can see they look a little bit similar, the one I wrote by hand and the one outputted over here. And yeah, here are like the symbol names. Here's the address that it's found at in the binary. When it actually gets loaded into RAM, this is the address that the instructions are going to be jumping into. Yeah. The point is, there is code hiding under what most of us would consider the lowest level, and I appreciated the complexity of that today. By writing assembly, like actually sitting down and writing it, I learned about alignment, static and dynamic linking, branching. I learned how signed integers work, which is a topic for another video. They might work a bit differently than what you expect here at the assembly level with the branching and whatnot. And yeah, this over here is, while it has some clever tricks, it's still far from an optimal assembly solution. And the compiler will definitely generate a better function if I turn optimizations on. For example, there are even bigger registers we could use for chunks, like over here. Like there are 32 byte wide registers and even wider registers that we can put loads of characters into, and there would be instructions to compare all of them at the same time and things like this, or just other optimized instructions for this application that I'm not aware of. And yeah, but the point is not to write fast code, what I was doing with this, and it's not even to write good code. I mean, good code is not always fast. While hiking in the mountains, you keep an eye on the straggler. That's the person you give the rucksack to carry. Um, then, when they're relieved of the rucksack, they walk the fastest. Writing this code was my rucksack, so to speak. Slow and laborious, but empowering afterwards. I love to write it and see it work. So, finally, over here, a shout out to this book I bought, Learn to Program with Assembly by Jonathan Bartlett. It has been an excellent read, probably my favorite computer science book so far. I highly recommend it to professionals and complete beginners alike. It's where I learned the stuff for this video, so go and pick this book up. It's absolutely great. Thanks for watching. Have a nice week.